So, you ever look up at a plane cruising at 30,000 feet and just wonder, how in the world is that giant machine actually put together? Well, today we're going to do just that. We're going to peel back the skin and look at the universal blueprint that ties pretty much all of them together, from the tiniest prop plane to the biggest jumbo jet.
I mean, just look at these two. A simple little prop plane and a cutting-edge fighter jet. They look like they're from different planets, right? Built for totally different jobs, different speeds, from different decades. But what if I told you that under the hood, they share the exact same DNA? That's the core idea we're digging into here.
Because it's true. There really is a universal blueprint when it comes to aircraft design. It turns out that almost every fixed-wing airplane you've ever seen is built from the same handful of major components, whether its mission is to train new pilots or to break the sound barrier.
And here they are, the 4 non-negotiables of building a plane. You've got the fuselage, that's the main body. You have the wings, the amazing surfaces that generate all the lift, the empennage, which is just a fancy engineering term for the tail that keeps it stable, and of course the engines, the powerhouse that gives it all a push. So let's break each one down.
First up, the fuselage. The easiest way to think about this is as the backbone and the body of the aircraft all rolled into one. It is the central piece of the puzzle that literally everything else attaches to. So the fuselage has 2 main jobs, and they're both absolutely critical. Job number 1, hold everything you want to take with you. That means the pilots, the passengers, all your luggage, and sometimes even the fuel. Job number 2, it acts as the main connection point, the hub that ties the wings, the tail, and the landing gear all together into one single, solid machine. From the outside, what we see is this smooth, sleek, aerodynamic tube. It's carefully shaped to slice through the air with as little resistance or drag as possible. It looks almost deceptively simple, right? Just this one elegant shape. But if you could peel back that smooth outer skin, this is what you'd find underneath. It's this complex, incredibly strong internal skeleton. This is where the real engineering magic is happening, a framework designed to handle the unbelievable stresses of flight. And the way we build this framework has changed a lot over the years. Way back, early planes used a lattice structure. You can think of it as a welded metal tube frame with fabric just stretched over it. Simple, but not all that strong. Then came the monocoque design, where the outer skin itself carries all the weight and stress. This is strong, for sure, but the skin has to be really thick, which means it's heavy. And that led us to today's standard, the semi-monocoque. This is the best of both worlds. You get a thin, lightweight skin that's reinforced by that internal skeleton of stringers and frames. It's crazy strong for its weight, which is why it's the go-to method for pretty much all modern aircraft. All right, next up are the wings, and their design is every bit as critical. Every single curve, every angle, every inch of its length and width, it's all a very deliberate engineering decision that completely defines how that airplane is going to behave in the air.
Which brings up a great question, right? We all know wings are there to create lift, so why the huge variety? Why does the wing on a slow, gentle glider look absolutely nothing like the wing on a supersonic fighter jet?
And this right here is the answer. It all comes down to a fundamental trade-off in aerodynamics. On one end of the scale, you've got wing shapes that are designed for maximum stability, perfect for a smooth, predictable flight. And on the complete other end, you have shapes built for pure, high-speed agility. Let's use some real-world examples. Think about a small training plane. It's got those straight, rectangular wings. They provide a ton of lift at low speeds, and they're super stable and forgiving. But for a fighter jet, you need raw performance. That's why you see those sharply swept back, almost triangle-shaped delta wings. You give up some of that low-speed lift for incredible high-speed performance and agility. Now, a key technical term you'll hear engineers talk about is aspect ratio. Put simply, it's just the ratio of the wing's length to its width. A high aspect ratio gives you those long, thin, graceful wings you see on a glider or a big airliner. They are incredibly efficient in making lift. On the flip side, a low aspect ratio gives you short, stubby wings, like on a fighter. They're less efficient at making lift, but they produce way less drag at super high speeds, and they're structurally stronger for pulling off aggressive maneuvers.
Okay, so we have a body to hold stuff and wings to create lift. Now we need to actually control this thing and keep it pointed in the right direction. And that brings us to the tail, or as it's officially known, the empennage. This is the plane's built-in guidance and stability system.
Honestly, the best analogy for the tail's job is to think about the feathers on an arrow. If you shoot an arrow without feathers, it just tumbles end over end through the air. The tail assembly does the exact same thing for a plane.
It gives it the aerodynamic stability it needs to fly straight and true.
But it also gives the pilot control. So let's break it down. The big vertical part, the fin, is called the vertical stabilizer. Its job is to stop the nose from wagging side to side. That motion is called yaw. The hinged part on its back edge is the rudder, and that's what the pilot uses to steer the nose left and right. Then you have the flat horizontal part, the horizontal stabilizer. It stops the nose from bobbing up and down, a motion we call pitch, and those flaps on its back edge are the elevators, used to point the nose up to climb or down to descend. So we've got all these major components working together, but maybe the real masterpiece of aircraft design is building a structure that is strong enough to withstand the unbelievable, invisible forces that are constantly attacking it during every single flight.
Just take a look at this. An airframe is never just sitting there peacefully. It's in a constant battle with physics. It's being pulled apart by tension, squeezed together by compression, and it's constantly being bent and twisted by the forces of the air rushing past it. Every single part, right down to the last bolt, has to be designed to handle these relentless stresses without fail.
And here's what's truly mind-bending. These forces completely reverse themselves between the ground and the air. When a plane is just sitting on the tarmac, the weight of its wings and engines makes them sag downwards. But once it's flying, the force of lift pulling up on the wings is so powerful that it actually bends the wings upwards. The structure has to be tough enough to handle both of these opposing forces perfectly, over and over again.
And this quote right here, this is the soul of aerospace engineering. The choice of every single material, from the wood and fabric of the Wright Flyer to the advanced aluminum alloys and carbon composites we use today, is a direct answer to the question, what specific stresses will this part have to deal with in the air? It's problem solving at its most fundamental.
So when you look at an aircraft, you're not just seeing a machine. You're seeing this beautiful, elegant collection of solutions to the incredibly complex problems of lift, control, and stress. Which leaves us with one final thing to think about. If every part of today's planes is a solution to a problem, what's the biggest problem the next generation of aircraft will need to solve? More efficiency? Quieter flight? Maybe even flying all by themselves? That's what makes this whole field so exciting to watch.